Let's continue with our equations of motion for ideal oscillations. And as a reminder, ideal oscillations are also called simple harmonic motion. Which sometimes you'll see that abbreviated as just SHM. All right, so our current author is using the generic equation that the position of an oscillating system, so mass on a spring is a common example, a pendulum swinging back and forth would be a common example. He's generically writing this as x of t, so x being the position from equilibrium. He writes this as a cosine omega t plus phi naught. So x of t is the position. The position of this oscillator at any moment in time is changing. As a reminder, A is amplitude, meaning the maximum distance the oscillator moves from its equilibrium position. Omega is the angular frequency in radians per second. So how many oscillations per second converted into radians per second. Phi naught is the phase constant or phase shift that accounts for the initial position of the object. So let's say we had a situation where we had our oscillator initially, so x naught, the initial position, was half the amplitude. So our graph, there's actually two different options here. So if we were graphing position versus time, this initial position is going to be half the amplitude. So A would be up here. This would be the initial position of 1/2 the amplitude. Equilibrium is x equals 0, so the mass would be oscillating or passing through its equilibrium position. So there's actually two situations that could be true. The mass could be initially at that halfway location and traveling upwards towards its maximum displacement on that positive side. So for example, since we have this labeled in terms of x, let's say we had just a mass spring system that was moving horizontally, and this was equilibrium. We're saying that at this initial moment in time, here's our amplitude, x naught is half the amplitude. So this mass is halfway between equilibrium and its maximum distance. The way I've drawn the graph, this mass is moving to the right initially because it's headed upwards towards that maximum displacement. Now, technically, the other option position versus time, that mass could be starting at the same initial x naught, but if the graph goes down, so the mass is not headed to its maximum positive position, it's headed towards the left. So it has a V naught that is negative because the mass is headed towards the left, headed towards equilibrium. So both of these have the same initial position, but they do not have the same phase constant if we were to write their equations out. So probably the easiest way to think about the phase constant, if you remember the last video, we were modeling and talking about the relationship between circular motion. I didn't draw this big enough, sorry. Let me draw it bigger. This would have to be a really big disc for my peg. So I'll just draw a portion of the disc. So the center of the disc is our equilibrium, and our peg has to represent, its shadow is representing where the object is traveling, which way it's going. And actually, I need to draw it, because if this disc is rotating counterclockwise, let me go up a little further. It has to be down here, that peg, so that as the disc continues to rotate this way, the peg will be headed this way towards that maximum amplitude, so that the shadow will line up to where it's headed. All right. In the second situation, if I move this a little bit, my disc, again, is going to have the center representing equilibrium. Our peg is needing to line up with where our mass is at that moment. In this case, since our mass is moving to the left, it's going to get back to equilibrium. I would actually draw my peg at the top, because this disc, we model it as rotating counterclockwise, it's headed towards equilibrium. In either case, phi naught represents this angle between where the peg is initially, at this initial moment in time, and how it is moving, where it is headed to. Okay. So to actually, calculate phi naught, we use our generic equation. Because it's kind of headed off the screen. So our generic position equation for these ideal oscillations, it could be written in terms of sine or cosine. I'm just going with what our author is representing. What we do to find phi naught is we plug in where the oscillator is at time equals 0. So at time equals 0, this example, we've said the position is 1/2 the maximum displacement, 1/2 the amplitude. So in place of x of t, so this x of t means the position at the moment in time we're talking about, I'm going to put in 1/2 a. I set that equal to a cosine omega, but I'm plugging in the value of the position at time equals 0. So I need to put in 0 for time. So that term disappears. I have 1/2 a equal to a cosine phi, that phi naught. In this particular case, because this initial position is in terms of a, I can cancel those a's. And so 1/2, this cosine of that phase angle has to equal 1/2. Now, because omega has units of radians per second, we want phi to be in terms of radians as well. So when I say that phi is the inverse cosine of 1/2 in this specific example, excuse me, my calculator needs to be in radian mode in order to get phi in radians. So I'm changing my calculator to radian mode. Now I'm going to take the inverse cosine of 1/2, and my calculator gave me a decimal number, or I shifted it over to in terms of radians just to make more sense out of it. This equation is telling me that phi naught is equal to pi thirds. But my calculator is not smart enough to know whether or not I need the positive pi thirds or the negative pi thirds. And so we have to put that into the equation specifically. And that's where this relationship, or relating this to circular motion, is handy. When we look at these two different situations, so this first situation, situation 1, the mass is headed to the right. We had to draw the peg down here at the bottom to represent it was headed towards its maximum distance. So if we think about the shadow of the peg up here, to get it to move to the right, we had to draw the peg at the bottom because omega, the rotation of that disk, is counterclockwise. Since now if we think just in terms of a coordinate system, an angle down from that positive x-axis is a negative angle. And so phi naught, this phase shift, would be negative pi thirds. Similarly, in situation 2, where the mass is at the same initial location but headed towards equilibrium, the angle is in front of, we have to move, well, that's a bad way to say it. And that's actually the wrong angle. Phi is, in either case, measured from this horizontal axis. So phi naught is still pi thirds. I drew it in the wrong place. I apologize for that. So it is ahead of this amplitude location. So when the shadow would line up with that maximum position. But the peg at this moment lines up with where it is. The rotation is going counterclockwise. And so this angle of where the peg actually is, so actual location versus amplitude, this angle is ahead of that. And so this phase shift would be positive pi thirds. And so when we would write out our equations of motion, we would put in our negative pi thirds here. In this case, we would put in our positive pi thirds. And that accounts for which direction the mass is headed in at that moment. Now, amplitude in either situation would need to come from the graph or the wording of the problem. So if we supposed we were given a graph, like I drew up here, we would be able to read this actual value on that vertical axis and figure out from that what the amplitude is, the maximum distance, either up or down, that the mass has moved from equilibrium. The period we could read off the graph as well. So we can read A and T, amplitude and period, can be obtained from the graph itself. And so A would go straight in there. The period comes into play in terms of writing omega. We know omega is the angular frequency in radians per second. We can write that as 2 pi f, the frequency. And frequency is 1 over period, and so omega ends up being 2 pi over period. So the period we can get off the graph, we can then calculate omega from that, and then we would just put those values in, and we would end up with an equation. I'm just going to make up some numbers. 0.33 meters cosine of 2.8 t minus pi thirds. Okay, I made those numbers up. This 0.33 meters would tell me that this mass, the oscillator, is moving a maximum distance of 0.33 meters from equilibrium. The 2.8 would be my omega value in radians per second. And phi naught tells me essentially the initial position. It relates to where the mass is at initial time t and what direction it is heading in at that moment. Okay, so again, I made those specific numbers up just to try to explain what we would end up with as an equation of motion. Which means we could then plug in anytime we want and find where that oscillator is at that moment in time. So any ideal oscillating system is going to have a position described by something along these lines, the A cosine omega t minus, plus or minus essentially phi naught. We ended up with minus in that particular situation. You can totally write the motion in terms of sine if you want. That's fine. Remember, cosine and sine are just different different initial positions. They're different phase shift. They're shifted from each other by pi halves, by 90 degrees. Our author just chooses cosine. Now, if we rewind our brains to early in our first semester physics class, we learned that if I have an equation for position, I should certainly be able to come up with the equation that describes the velocity. The velocity of an object as a function of time can be calculated by taking the derivative of the position of the object with respect to time. So I'm taking the derivative of this x function with t, with time, as my variable. I could write it this way, d dt, and then put in this function I'm taking the derivative of. The t tells me the variable that I'm taking the derivative with respect to. So when I take this derivative cosine is sine, so I'll have sine of all this stuff. But then chain rule, I have to take the derivative of what's inside the cosine term with respect to time. So, derivative of cosine is negative sine. So derivative of this inside stuff is just going to be omega. This tells me that if my position equation is this cosine function, then my velocity equation is going to be, let me draw that better. A times omega, and then times the function of sine omega t plus phi naught. So omega is the same thing, phi naught is the same thing, A is the same thing. This would describe the velocity. This would be the equation for the velocity as a function of time. So our cosine function, if our oscillations, if our position was exactly perfectly a cosine function, our velocity in this situation, so if the position was perfectly cosine omega t, then the velocity would be negative a sine omega t, meaning at 0 moving down. What this tells me is when x is a, when the mass is at its maximum distance from equilibrium, the velocity is 0. When x is 0, so if x is 0, the velocity is the absolute value of the velocity is a max. It's the biggest value it can be. This is essentially the amplitude, not a, but when we talk about a sine or cosine function, amplitude of the velocity function. The maximum value. If we come back and look at this equation for velocity, the sine portion, sine and cosine, always has a maximum and minimum value of 0 to 1 or to negative 1. And so the maximum value of v is whatever is out here in front of the sine function, a times omega. So this is the maximum speed. If you remember, velocity is just how fast and in what direction. So the maximum speed is the same whether we're talking it being in a positive direction or a negative direction. The speed is maximum when the mass is moving through equilibrium, which hopefully makes sense. So let's jump over back to our oscillating systems. Let's go back to the mass spring. Let me slow it down again. If we watch this graph, that kinetic energy term is biggest when the speed is biggest. That happens as this mass moves through this equilibrium position. The spring gets stretched more. That means there's more potential energy, which means the spring is slowing the mass down to stop it. There's a split second in which the mass actually stops, which means the kinetic energy would be 0. All the energy is potential, and that potential energy starts turning back into kinetic. So whenever the mass is at its maximum distance from equilibrium, it's turning around. That's the moment it stops for a split second. It's turning around to head in the opposite direction. So when the mass is located at its maximum distance, its amplitude, the speed is 0. And conversely, when the position is 0, the velocity or speed is maximum. All right. Well, if we take the derivative to get to velocity, we can take the derivative of velocity to get to acceleration. So the acceleration of this oscillator as a function of time is going to be the derivative of the velocity function with respect to time. So the derivative with respect to time of this function we just came up with derivative of sine is cosine, and again we have to take the derivative of that inside portion. We ending up with another omega, so we get omega squared out front. And our acceleration equation ends up being negative cosine function. If this is equilibrium, if we come back to this situation, if the position function was just purely cosine, the velocity ends up being negative sine, the acceleration ends up being negative cosine, meaning it's a negative maximum value to begin with, and then oscillates from there. So if we come back here, when x is a, meaning the mass is at its maximum displacement, velocity 0, coming down here, acceleration will be a negative maximum value. It's a negative value, just meaning it's headed in the opposite direction compared to the position, which hopefully makes sense. If my mass oscillating up and down, if it's at its highest point versus its lowest point, up here the position, x is positive, but the acceleration is negative, meaning there's a net force pulling downwards on the mass. If the mass was all the way down here, its position would be negative because it's below equilibrium, but the mass itself is experiencing a net force upwards. The acceleration will be positive. The acceleration is always opposite the motion. We call this situation, there's some sort of restoring force. The forces, the net force on the object is always trying to bring it back to an equilibrium position. Okay, so one other little thing in here, if we come to the function for acceleration, the quantity out in front of the cosine represents the maximum value of this function, which is the acceleration function. So the maximum acceleration, the magnitude of it, will equal the amplitude times that angular frequency squared. So we have these two relationships that allow us to calculate the maximum values of the speed and the acceleration. And those are true, those relationships are true regardless of where the starting point was. The negative sine versus positive cosine, negative cosine, that's independent of the value we get in front. So these two equations right here are always valid for this ideal simple harmonic motion. Whether the function's sine or cosine, or negative sine, negative cosine, if it has a phi naught, a phase shift, that just changes finding the values of position, velocity, or acceleration at specific moments in time. So we'll be doing some examples that relate to these oscillations and these equations. And then we'll also be talking about the specific situation where we have a mass on a spring or a pendulum. So those videos will be coming up.